Okay, what would you like to address? Do you have it? Okay, what is it? Mm-hmm. Mm-hmm. So n squared? Okay. N equals 1 to infinity? All right. So what were you thinking on this? The root test? Yes? So the root test says that if I take the limit as n goes to infinity of the nth root, right? The nth root of 1 plus 1 over n to the n squared. If that turns out to be what? Well, I mean, what are my conclusions? It's kind of like ratio test conclusions. Greater than 1, diverges, and equal to 1, inconclusive, right? Yes. Okay, so what were you thinking about this n squared? Like, how are you going to want to deal with this? I guess let's just look at what does this mean? I mean, this means x to the n times n, right? We can say it that way, right? Agreed? Now, how could I get that writing it a different way? X to the n. Okay, what's this? What's that? Because you're doing what? Multiplying 2 times 3? So couldn't I do x to the n, like that? That's x to the n times n. This is x to the n times n, which is x to the n squared. Yes? So what I would like to do is rewrite this, and just because of time, I will erase this. I'll put this all in parentheses, and then to the n, like that. Is that okay? That's the whole thing to the n, but then all of that to the n again. So this is the same as like the x to the n to the n. Now, when you take the nth root of that, the red power goes away, right? So what you're left with is limit n goes to infinity of 1 plus 1 over n to the n. Now, we cannot do, I think you said do root test again. The problem with that is that this is not a series. So you can't do the root test on a limit. So if you have a series, you can look at the a sub n, right? This was our a sub n right here. And you can do the root test on the absolute value of a sub n. That's what the root test says. But applying it again means that you would have to be looking at another series, which you're not. However, this is a limit that can be done using just calculus 1 techniques. Just call this whole thing y, let's say, and then take ln on both sides. And when you do that, the natural log can pass through the limit. So I take the natural log on this side right here, and I bring the n down in front of the natural log, which is the whole reason you would do that. So the n comes down in front, multiplied natural log 1 plus 1 over n. I know we've done something like this before. And so now what you have is infinity times, if you do this, it's 0. And I'm not going to go through this, but if you work through this whole thing, you should get y equals e. Go back and look in your notes. I'm sure I've done that. Y is e. Okay, yeah, no, this is a great question. It's a great question. I'm glad you asked. Because some people, have trouble with that n squared. Like, what does that really mean? So if this comes out to be e, that means this limit is e, which means e is greater than 0? I mean, sorry, greater than 1, right? E is greater than 1. So if E is greater than 1, I guess what I'm trying to get at here is this limit turns out to be E, right? So that's greater than 1, so this is divergent. The back of the book just says divergent, right? I mean, it doesn't say anything else, right? It doesn't have any other details. Yeah. Okay, any others? All right. Okay, can you tell me what it is? Wait, let me see it. Oh, okay. So it's 1 minus 1 times 3 over 3 factorial plus 1 times 3 times 5 over 5 factorial minus 1 times 3 times 5 times 7 over 7 factorial plus dot, 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 dot. Yes? So it's asking you for what? If it converges or diverges? Right, so what are your ideas here? Okay. Okay. But okay, so yeah, we have to figure out what's going on. Do you agree that the bottoms, okay, it's alternating, right? Okay, it's an alternating series. It's starting with a positive number. I'm trying to come up with a series representation of this. It starts with positive, so I go -1 to, I can do n minus 1 or plus 1, doesn't matter. That's if I'm starting my series at 1, right? So if I plug in 1, I'm going to get a positive number, and then I'll get negative, positive, negative, positive. That takes care of the alternating. Now, the denominators I think are a little easier to pick up on. This is a 1 underneath, then a 3, then a 5, then a 7. Those are factorials, but they're odd factorials. So I just need to create odd numbers and then do a factorial. So the odd numbers are 2n plus 1 or 2n minus 1, whichever one you want to use. In this case, we would want to use what? 2n minus 1, the way I have it written, 2n minus 1 factorial, right? If I plug in 1, I get 2 minus 1, which is 1 factorial, which is this. And I plug in 2, I get 4 minus 1, which is 3 factorial, which is this. Plug in 2, and so on and so forth. But what about the top? That's the tricky part. What's that? Did anyone get this? Yeah? Okay. How do you write it? How do you mean? A factorial and then another factorial? Okay. That's right. Okay, so let's see if that makes any sense. So you're saying 2n minus 1 factorial, but then factorial of all of that? Is that what you're saying? Let's see if that makes sense. All right, let's see. We haven't seen this yet, right? Okay, so let's see if it makes sense, and then we'll talk about where it came from, all right, if it makes sense. So if I did this, what would happen if I let n be 1? What would, it'd be 1 factorial, right? Which is this? So it would be 1 factorial, right? Which would be 1 factorial, which is 1. So that matches, all right? N equals 2 would be what? 2 factorial, which is 2 times 1 factorial. Is that right? Oh, I'm sorry. I was just doing factorial. I forgot we were plugging in here. My bad. This is 3. Sorry, 3, right? Factorial. Yeah, we're plugging 2 into this. So you get 4 minus 1 is 3 factorial. So there's 3 factorial, but then factorial. So that's going to give you what? 3 times 2 times 1 factorial. Is that what you're saying? Did I write this the way you want me to write it? What do y'all think? Yeah? I'm just a little skeptical because this, if you write it like this, then when you plug in n equals 2, you get a what, a 3 in here, 3 factorial, and then factorial again would mean first you have to figure out what 3 factorial is. 3 factorial is 6, and then this would become a 6 factorial, which would be 6 times 5 times 4 times 3 times 2 times 1, which is not what I have up here, right? Do you agree? Anybody have any other ideas? I mean, isn't this almost 3 factorial? Isn't this almost 5 factorial? Isn't this almost 7 factorial? What's missing? The evens are missing, right? You need to be able, so look at it this way. If I had, I'm going to take, let me take this one right here. Just look at that one for a second. If I have 1 times 3 times 5 over my 5 factorial, right? That's what I want to be there, right? It would be easy for me to be able to write this out up top with the 2 and the 4 in there, right? That would be 5 factorial on top. So I want to be able to take out 2 and 4 from this, right? Divide through, or I cancel it out somehow. Which one? For which one? 2n, say again? I'm missing what you're saying. No? I'm sorry, I'm not, no, you want? I think this might turn into a bonus question. This is good. Minus 2n would take away, it wouldn't divide through. This is a good one. I like this. It's not obvious. Is this an odd? It's an odd problem, but that doesn't help you because you don't have the. We need the formula though, right? I mean, we need to come up. Are you just waiting to see what happens? No, go ahead and go. I mean, well, if you come back and you miss anything, we'll tell you what happened. So let me tell you what happened. I'm kidding. I'm kidding. All right. Yeah, let me offer this as a bonus. You like bonuses, okay? I don't want to give this right off the bat. This is a good problem. I mean, there's something happening up here, and I don't think I ever gave you a series like this where, I mean, we had factorials in there, but we never had factorials missing pieces like this. And I'd like to see if you can come up with a way to make it happen. Now, let's make it a bonus to be turned in next class, all right? I don't want us sitting here focusing all of our energy on this right now. It's a bonus question to be turned in next class. And what I'm looking for is the formula that's going to give us this, all right? Do a little research on it, all right? Look in the book, look online, see what you can find. If no one can get it, then I'll talk about it next time. But let's talk about the test. So, I've had a couple of emails about what we're going to do with the test and, days and everything else. Here's what we're doing. It's a take-home test, and it's due on Tuesday. Now, that kind of probably ruins your weekend a little bit, but here's the thing. I'll give you the option of turning it in on Wednesday of next week also. All right, but let's just say this. If you turn it in on Tuesday at the beginning of class, then you can get 100 on it. All right? If you turn it on Wednesday, it's a 5-point deduction. All right? So you can have the extra time, but you'll lose 5 points for it. And so it'd be due on Wednesday, let's say 3 p.m. Wednesday, 4 p.m. Let me see, what's my Wednesday look like? I'm going to be here all day. 4 o'clock Wednesday. All right, it's 10 problems. I did not try and pick the hardest problems I could find. The first 8 are all convergence, divergence problems. 9 and 10 are what we're going to do today. All right, and so the reason I chose this is because, I just felt like to give you a good set of problems, this would be hard to do in an in-class setting, and I would rather not eat up a day for a test. I'd rather give you this. Now, this stuff will appear again on the final. So during the final, you'll have to do this without your notes and the internet and everything else you've got, right? Wolfram Alpha. So make sure you work on understanding this. Now, I will also say we have a couple of quiz grades, right? We need quiz grades in this class. So what I'm going to do is I'm going to offer you some quiz grades. Let me show you how I'm going to do this. For your homework from we're in chapter 8, right? What was before this? Did we do 7? How much of 7 did we do? Yeah. Okay, if you turn in your chapter 7 homework, your homework for chapter 8, now this doesn't have to be like complete every problem done. What I want to do is just look that you've been doing your work, all right? If it's all, hopefully it's all in some sort of nice place, all right? Turn those in separately, though, or somehow be able, like if they're in a spiral or something, make it so I can distinguish what's what, like where's chapter 7, where's chapter 8. I'm going to count that as 2 quiz grades, all right? So if you've been just keeping up with your homework, it's 200s. It's not a big deal. But if you haven't been doing your homework, you're either going to be doing a lot of work in the next couple of days, weeks, or you're going to not going to do it and you're going to get zeros, whatever, right? That sound fair? All right, it's just a homework check. Let's say those will be due when we get back from Thanksgiving, all right? When we get back from Thanksgiving. So these are due Tuesday, what is that, the 2nd? And then the take-home exam is due Tuesday, the 25th at 11 a.m., right? Or Wednesday, 11/26, 4 p.m., to be turned in Juniper Hall 111A. That's where my office is. Now, a little bit of warning. If you're going to drop it off, I may not be there. If I'm not there, you should get evidence that you turned that in. In fact, I would make a copy of it, all right, before you turn it in. Scan it, take pictures, whatever you have to do, because it has happened in the past that tests have been lost. In fact, I lost one this semester. It's the first time it's ever happened that a test disappeared, all right? So I have to have evidence that you turned it in, and I have to have evidence of what you turned in. So if you're going to take the risk of doing it while I'm not there. Now, I will be in my office on Wednesday from 3 to 4. Yeah, 3 to 4. Okay, does that sound fair? Oh, I forgot to say 5-point penalty. Deduction, we'll call it a deduction. And then what did I say about the bonus? Bonus next class also. Now, the way I've normally done bonuses in the past is that the more people that turn it in correct, the less it's worth. All right? So if everybody turns it in correct, then it wasn't really that much of a challenge, and so it's not worth a whole lot. So also, if you figure it out, don't be like, hey, calling everyone, come here, I got it, here, show everyone. That defeats the purpose. The purpose is that you figure it out, right? So if you get it, don't share it. Turn it in. All right, this all clear? Now I'm going to hand the test out. Please remind me at the end of class, because I don't want anyone to be working on it while we're talking about the stuff today. Are y'all ready to get going? All right, so last class I had given you a handout, right? And we had talked about how there was a theorem, wasn't there? That's where I ended, this theorem. I said that if you're given a power series, what are the three possibilities for the power series? If someone gives you a power series, n equals 0 to infinity, c sub n, x minus a to the n, what are the three possible outcomes here? It converges when x is a only, right? Meaning that's the only place it converges. If x is a, the power series is 0, isn't it? So that's kind of what we would consider to be the trivial solution. Like, that's the trivial case, that if you let x be a, it converges. Okay, so it's going to do that, or it'll do this, converge for all x in the real numbers. In other words, for any real number x that you plug in, doesn't matter what it is, the series converges. And then the last thing, or there is a number r such that if the absolute value of x minus a is less than capital R, it converges. If the absolute value of x minus a is greater than R, it diverges. And what is R, that capital R, called? Radius of convergence. All right, that's in your notes, right? I handed that to you last class. Now, also, if we take this absolute value inequality, sorry, this one up here, if we take this absolute value inequality and we drop the absolute value and write it as, what it means x minus a must be between two things, negative R and positive R. And if we solve for x here, in other words, get x by itself, adding a to both sides, or both inequalities, then what we get is that x must be between some number plus another number, right? Well, negative R plus a is a number, and then R plus a is a different number. So what we get is an interval. And so what we're saying is that as long as x is between these two numbers, it's going to converge. And this right here is called the interval of convergence, which is what we're going to spend most of our time on today, is determining the interval of convergence for a power series. What has not been addressed in these two inequalities? What if it's equal to R, right? What if this absolute value of x minus a is equal to R? And so we will have to address that. We will have to address that. And it's going to be, as you'll see, a little bit of work, but not too bad, all right? Any questions? We're gonna use this theorem, but keep in mind, you cannot have two of these things happening at the same time. You can't say it converges on an interval, and then it only converges at x equals a. It's got to be one or the other. It cannot be multiple, all right? Does that make sense? All right, let's look at our first example. Find, I'm going to say, radius of convergence and interval of convergence of this power series. Why do we call this a power series and not just a series? Because we have x to the n, right? If there was not an x in here, and it was just negative 5 to the n over square root of n plus 1, it would just be a regular series that we were studying in the previous section. What we've added into the whole mix here is this idea of this variable x that has powers, right? And that x determines whether or not this is going to converge or diverge. It's going to matter. It is the thing that matters. In fact, we even said last class that we could define this as a function, and everywhere that for every x in which this thing converges would mean that function is defined. So we would really be saying that the interval of convergence is actually the domain of this function. It's the x's that make it converge. Okay, so let's get to this. Now, the most common test used for this is the ratio test. And the reason why is because a power series will always have powers, right? It'll always have x to the n. So the ratio test is really good for power series. So what I need to do now is do a ratio test on this. To see where it converges. Well, remember, the ratio test says if I take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, I need that to be less than what for it to converge? Less than 1. So that's what I'm going for right now. I want the limit as n goes to infinity of a sub n plus 1, absolute value. A sub n plus 1 would be negative 5 to the n plus 1, x to the n plus 1 over square root of what? N plus 1 plus 1? So n plus 2? That's a sub n plus 1 divided by a sub n. But we said that that's always going to happen, so we just multiply the reciprocal. So what's a sub n here? Written, flipped over. Root n plus 1 over negative 5 to the n, x to the n, right? Absolute value. All right, now, what am I going to do? Oh, I want this less than 1. Sorry, I want that to be less than 1, don't I? I'm asking myself this question. When is this ratio less than 1? If I can figure out where that ratio is less than 1, then I've determined where it converges. Yes? So what do I do? Start trying to get rid of stuff, right? Everywhere we see these powers, n plus 1, we peel it off, right? We split it up. So we can write this as limit n goes to infinity, absolute value, negative 5 to the n, then what? Negative 5. It'll still be negative. Whatever that base is stays the same. So negative 5 to the n, negative 5, and then x to the n, and then x all over. Nothing changes down here. Over here, nothing changes. And now we get some good cancellation, don't we? Negative 5 to the n cancels out with negative 5 to the n. X to the n cancels with x to the n. And now I'm gonna figure out. Oh, I want this less than 1. I'm gonna figure out what all this turns out to be. So I have x here, right? That's the only thing. That's the only thing that has x in it. Then I've got this -5. I've got this root and this root. I'm going to take an absolute value at some point, right? So that -5 is really going to turn into a +5, isn't it? And then the absolute value of a square root and a square root, those should both be positive also, right? Because n is positive here. So I won't have to worry about signs on that. But x, I have to worry about. X could be negative, right? So I will have to keep that absolute value on the x. So watch what I write on my next line. Limit n goes to infinity, 5 root n plus 1 over root n plus 2 times the absolute value of x is less than 1. Do you agree with that? So I've taken the absolute value off of everything that I know didn't need it anymore. Well, I took the absolute value of -5 and got 5. The roots are here. Notice I've separated the n stuff from the x. All right, now, the reason I separated it is because I want to know what happens when n goes to infinity, right? N is not actually affecting the x at all. N's only messing with this. So for this, we have infinity over infinity, right? So you could do L'Hopital's rule, though I wouldn't recommend it. I would instead probably do this. Rewrite that as 5 root n plus 1 over n plus 2. So just using properties of radicals that if you have a root on top, root on bottom, you can put them into a fraction like this. And then look at the inside there. What happens is n goes to infinity there. Infinity over infinity. So do a little quick L'Hopital on that if you want. It's going to be 1, right? Square root of 1, and then you have a 5 out front. So all of this, when I apply the limit, all of this is going to turn into a what? What is that going towards? What is that converging to? 5, right? 5. So this is really, I want my 5 absolute value of x to be less than 1. Limit's gone, right? I let n go to infinity. The limit is gone. So what will happen is this thing will converge as long as 5 times the absolute value of x is less than 1. Now, first thing we want to do is find the radius of convergence. The radius convergence is you have absolute value of x minus a is less than capital R, right? I need to have my final inequality look like this. Absolute value of x minus a. For us, a is 0, right? And I don't want anything out in front of the absolute value. So I need to get that 5 out of there. So I divide both sides by 5. Once I have my absolute value of x isolated here, I now have attained what R is. R, the radius of convergence, is what? 1/5. Okay? So I've answered one of the questions. You okay on that? That means that the radius of convergence means that I have some point, right? And if I look at a radius, it's in each direction, okay? 1/5, 1/5 each way. That within that 1/5 each way, this power series converges. As I know there's still some question as, you know, what we mean by that, but just bear with me for a minute. I'm going to show you a picture and hopefully it'll all come to light. All right, so that's our radius convergence. Now, what's our interval of convergence? So go to the next page, and what do I have? Rewrite this as a string of inequalities here, and this is -1/5 less than x less than 1/5. That's what we mean when we say the absolute value of x must be less than 1/5. Agreed? Now, you may think you're there. You're almost there. The question we still have is these inequalities were strict inequalities because for the ratio test to work, it had to be less than 1, right? If it was 1, it was what? Inconclusive, right? That doesn't mean it didn't converge. It's just we didn't know. So what would happen if I actually let those be equals? And so what we're going to have to do is check each one of the sides. I'm going to have to say, what if x was allowed to actually equal -1/5? And then what would happen if I actually let x equal positive 1/5? Look at those two different scenarios and see what would happen. Understand? So I have to check these now. I have to check the endpoints. Oh, sorry. Left my phone on. So check endpoints. So first let me start with the negative one. Let x be equal to negative 1/5. Does everyone understand what I mean by I'm checking the endpoint? I'm seeing if those inequalities are going to be strict inequalities or not. So if I let x be negative 1/5, go back to the original power series and replace x with negative 1/5. So rewrite the power series the way it was given. Sum n equals, what was it, 0 to infinity. It was negative 5 to the n, but then it was what? X to the n? So that would be negative 1/5 to the n all over square root of n plus 1. That's the original power series, replacing, right? Replacing x with negative 1/5. Now, since the negative 5 is raised to the n and the negative 1/5 is raised to the n, I can put those together, right? And that's negative 5 times negative 1/5, which is 1. And 1 to the n is 1. So this series now becomes something we did in the previous section. See, x actually is taking a value on. Once I give a value to x, we are looking at something from the last section. Does that make sense? And now you have to answer the question of whether or not that converges or diverges. So, any ideas? What's that? Maybe a comparison test with a p-series 1/2? Yes? So now you have to utilize your methods from last class to figure out if this converges, or last section to see if it converges or diverges. Now, should we do the comparison or not? Do you want to see a comparison on this or not? I mean, or can I just say, by some test, it diverges? You can't do that on your test. You can't do that. You have to show it. But do you want me to show it right now or not? Yes or no? Yeah. Yeses? Okay, that's enough yeses. All right. So on this one, you're thinking p-series. So comparison test. I'm just going with what I'm being told here. It seems like a pretty natural thing to do. We are comparing the sequence, a sub n is that, to, you wanted to compare it to what sequence? 1 over root n, which is the same as 1 over n to the half, which is a p-series, with p being less than 1, which means it diverges. So you're wanting to compare it to a divergent p-series. Now, do you want me to do the comparison where I use the inequality, or do you want me to do the limit comparison? Because remember, there was two ways I could approach this. Limit comparison, I think that's probably going to be the best one. Let's see. The limit comparison says, if I take the limit as n goes to infinity of the absolute, well, no, you don't need absolute value because these are both positive. What is it? A sub n over b sub n. I'm looking off of, there it is, our sheet, right? It's underneath comparison test. It's the third one, right? If the limit n goes to infinity of a sub n over b sub n is equal to c greater than 0, but c has to be what? Did we say c has to be finite? C is a constant, okay? You might want to put a little note on that 3, that the limit comparison test, that where it says c greater than 0, that c has to be finite. All right, so This needs to be some number greater than 0. If it's a number greater than 0, then my conclusion is that whatever they do, they both do. So if I know that this one diverges, I know the other one has to also. All right? That's the idea here. Pardon me? If it diverges, if it does, that means the negative 1/5 will not be in our interval of convergence, right? Because by letting x be negative 1/5, it created divergence of the series, which means we don't want it because it's an interval of convergence, not divergence. Good? Okay, so let's do it here. This is limit n goes to infinity of a sub n, which was the one we were trying to start with, over 1 over root n, which turns out to be limit n goes to infinity of root n over root n plus 1, which is just 1. I'm not going to go through it, but that's just 1. And that's greater than 0. Therefore, whatever the series with b sub n, right, whatever this series does, the other series must do the same. So therefore, letting x be equal to negative 1/5 causes divergence. So we don't want to include it. That makes sense? We don't want to include it. We don't want to include negative 1/5 as an answer because it creates divergence of the series. Now we have to do the same check, right, for positive 1/5. Got it? Any questions on this? We're only halfway done with the testing of the endpoints. You can almost see how if I were to pick a nice enough power series, I could kind of knock out all the comparison tests or all the different tests at the same time, because I could force you at the endpoints to have to do these different tests, right? I'm not going to do that. I'm just saying I could. Okay, let's let x be equal to positive 1/5 now. So what does our series become? Yeah, it's negative 5 to the n, but this time it's positive 1/5 to the n over the square root of n plus 1. That, this time, when I put those two together, I'm not going to get the positive anymore, right? It's not going to be positive 1. It's going to be negative 1 to the n. And so now I have an alternating series, don't I? And when you have an alternating series, you can try the alternating series test, or you could also try the ratio test, couldn't you? You could also try, I mean, you could try different things. But I think the alternating series test is probably the best one to go with here. The alternating series test says that I first need to be able to rewrite my series in this form. I need to be able to like peel off the negative 1 part and write the other part separated. And that's the part of the alternating series test that I call the a sub n. So you separate the alternating negative 1 thing away from everything else. And then what are the two things I have to show about this a sub n? What's the first thing I have to show? It's decreasing. Okay, I want to show a sub n is greater than or equal to a sub n plus 1. What's the second thing I have to show? The limit as n goes to infinity of a sub n must be 0. So I have to show those two things. If I show those two things, it means that that series converges, doesn't it? And I think it's going to work, right? Is it decreasing? how could you convince me that this is decreasing? You could try and set up the inequality, right? Is that greater than or equal to this? Cross multiply? Oh, I said it again. Oh, here's something dangerous. If you square both sides of an inequality, does it maintain the inequality? Does it maintain the inequality? If I square it? If this is bigger than this, right, then when I square it, is it bigger than this? We had talked about, well, maybe we didn't talk about this, but tell me if this is true. Is 1/2 bigger than 1/3? Yes? If I square them, what do I get? 1/4 bigger than 1/9, right? Still okay? Yes? All right. If I take numbers that are bigger than 1, 3 is bigger than 2, right? If I square both sides, 9 is bigger than 4. That looks good. This is going to hold. It's going to hold, but I just want to make sure you're thinking about it, that it's not an equation, right? It's an inequality, so you have to consider it. Do you remember ever in like a calculus, in the Cal 1 class, maybe where you're trying to find like a minimum distance? These are like in some of the application problems. And instead of looking at the distance, you looked at the distance squared instead. Because you didn't want to mess with the square root, so you squared it instead. This same principle is that if you have an inequality, if this is always bigger than this, you square it, it'll always be bigger than the other side also. So we can do that. N plus 2 greater than or equal to n plus 1. 2 is always greater than 1. That's true. So I'm happy with that. The next thing is obvious, right? That limit checks out. Do I even need to do that? Fixed over infinity goes to 0, so that's good. Uh-huh. You don't have to do them in that order. Okay. Yes. Yep. Everyone understand the question? You could do either one of those first, especially if you felt like this wasn't going to go to 0. Then you might want to do that one first so you can see that. And then once that doesn't happen, you just throw this out. Okay, so what is our conclusion? Therefore, x being equal to positive 1/5, right, causes what to happen? Convergence. So we do want it, right? We do want to include it. So what is our final interval of convergence then? Negative 1/5, less than x, less than or equal to 1/5. There we go. Like a bracket? Yes, you can. You can write it like this. I'm okay if you put something like this, negative 1/5 to 1/5, like this. It might be better if you put out there x is an element of that set so that people know that you're talking about like x belongs there. If x is in there, it's good. That's our interval of convergence. Okay, let's see if I actually had that series up here or not. No, I didn't. All right, next one. Whoa, that was it? No. Was that it? Were there more examples on there? Did I skip something? That was it? You didn't see this example? I don't know where the heck I pulled that example from. Well, it was a good exercise, right? All right, well, let's get back to the ones that were on here. Is the next one that you have the, did we do the 2x minus 5 to the n over n? Did we do any of them? No? Okay, did we do this one? I've got like 2 sets of notes up here. I think that's my problem. I have notes from 2 different semesters. Ah, there it is. That's what I gave you. Okay. How about this one? Do you have this one on there? Sum n equals 0 to infinity 2n plus 1 x to the n over n factorial? We did this one. Yes? But we didn't check the endpoints, did we? We didn't check the endpoints on this. So let me refer back to last class. Let me just see what I had here. Yeah, okay, so from last class, let me just go through this real quick because we've done this. This was it right here. We set up the ratio test. We went through the ratio test. When we did it, what we got at the end here was the limit with the n part of it, and then we had the absolute value of x here. We needed this to be less than 1, but this goes to 0. And since this goes to 0, it doesn't matter what x is. And it kills off the x in this. That means it doesn't matter what x is. And so if you can, it'll always converge, which means that our interval convergence is everything, all real numbers. That's why we didn't have to test endpoints on that problem. Right? Do you see? From the theorem, I've shown you an example of 2 of the 3 cases, haven't I? One where you have an interval of convergence, you have to test the endpoints. The other one where the interval of convergence is all real numbers. The key difference is what? What happens here, right? That piece right there is going to dictate whether or not you have anything left to work with. What if this limit right here becomes infinite? What if it becomes infinite? What if this limit right here is infinity? Then it diverges, right? It's bigger than this. No matter what x is, it's going to be bigger than 1. So it'll diverge everywhere, right? Except where? When x is equal to a, right? In this case, when x is 0. If x is identically 0 here, the whole sum is 0. So that would be the third case. Understand? This piece is the key to the whole idea of a power series. What determines which of the 3 cases you're in is all dependent on what happens to this limit right here. If this limit is 0, your interval is everything. If this limit is infinite, then it's only when x is a. If this limit is a number, you got to go get endpoints and work it out. All right? Make sense? So let's do a different one. Not that one. The next one we had was the 3x minus 4 one. You have that on yours? All right, so what about 3x minus 4 to the n over n squared plus 1? All right, so this is a power series. Notice, though, that I don't have just x to the n, right? I have 3x minus 4. Are you raising your hand? Yeah. It starts at 1, doesn't it? Okay, we'll start it at 1. That shouldn't affect our convergence or divergence here because it's just one term and it's defined still, but I'll stick with what's on the sheet there. Right? If n is 0, it's still defined? Okay. All right, well, ratio test, right? Let me start with that. Let's see how quick you can write this out. Limit n goes to infinity, a sub n plus 1. 3x minus 4 to the what? n plus 1. Can I write that now as n times 3x minus 4? Can I just do that all in one step now instead of having to write it down? This is 3x minus 4 to the n plus 1. That's it right there. All over n plus 1 squared plus 1. And then times the other side flipped over, or the original flipped over. I need that to be less than 1. That's what I need for convergence to happen. Cancel out some stuff here. That's all it cancels, huh? So what I'm left with here is a limit. Let me try and get all my n stuff together. I have n squared plus 1 over the bottom is n squared plus 2n plus 2 times 3x minus 4. Say again? We're okay? So I just expanded out the n plus 1s, right? Squared it, and then added the 1 out here. And everyone okay with that? So what is this limit going to go to here? 1, right? 1. Because you got infinity over infinity, you apply L'Hopital's rule, you apply it again. Or did any of you learn in college algebra when you have a polynomial and they have the same degree, that it's just the leading coefficients divided by one another? That's all it is, but as a calculus student, we should know that, that's great if it's polynomial over polynomial, but if it's not, we have to have something else, right? So we just do L'Hopital twice, and it's good. Right, so that's going to go to 1. So what will be left after this limit is gone, and it's gone to 1, is the absolute value of 3x minus 4 must be less than 1, right? So let's go for interval of convergence. I'm never going to ask you for radius of convergence. On test, interval of convergence is all I want. So let's just go and rewrite this as an inequality. Is that okay? Rewriting that as an inequality? Let's try and get x in the middle here by itself. So I'll add 4 to everything. That look good? Divide through by 3. Any questions? I know that if x is between 1 and 5/3, it's going to converge. The question is, what happens at 1 and what happens at 5/3? So I have to go take a look at that. You ready to look at that? I need to check x equals 1 and x equals 5/3. So if x is 1, my series becomes what? Negative 1 to the n over n squared plus 1. I can already look at that right now and know it's going to, the alternating series test is going to work, right? Moreover, that is an absolute, well, it's absolutely convergent. If I take the absolute value of it, right, it's similar to a p-series with p being 2, which is convergent. So this time I'm not going through the work. You would have to show it, all right? Especially on a take-home test. You got to show the work, all right? So you can't just say, oh, that's like a p-series, it converges. No, show me it converges because of one of those tests. But I'm just going to say this converges. So we will include x equals 1. Yes? So include x equals 1. All right, what about x is, 5/3? If x was 5/3, this series becomes, you're plugging in 5/3 for x. I didn't do it on the last one. I didn't show it. I figured you could get that yourself. But isn't that just 1 over n squared plus 1? Yeah, a comparison test with n squared, right? Converges. So include x is 5/3. So your interval of convergence includes both endpoints instead of like last time it was include one, not the other. And it turns out you could have all the different possibilities for an interval to happen. You could have a truly open interval where you don't include the endpoints. You could have a half interval, like half closed. We call that half closed or half open. Doesn't matter. You can call it either one. You could have it the other way, or you could have truly a closed interval. Yes? Yeah, you need to convince me like it's its own problem. Yeah, like that series is a brand new problem. You would show the comparison test, though. You would have to show it. Oh, you mean as far as all the detail of that? Yeah, I mean, write it like you're writing a English paper, a report you're turning in. You know, make it thorough. It's a take-home test for your take-home test. Yeah, if it's an in-class test, I might be a little more lenient. But here's the problem: on an in-class test, did I say on a take-home test? In-class test, if it's wrong and you're not telling me what you're doing, or you're drawing a conclusion that it's not correct and you're not explaining it, then I'm not going to be very lenient, as opposed to someone who is explaining it but it's messed up. That I give them something for at least trying to explain what they're doing to me, you know. So show everything, and then so our interval is what? X is between 1 and 5/3, inclusive. Let me bring this one up. I want to show you that. See if I have. This is it right here. We said that if this is our power series, right? We said that if x was between 1 and 5/3, it should converge. So I'm going to make it less than 1, right? And now I'm going to have the computer start adding them up. And notice right now they're adding up to be negative 1.25. If I start adding these up, you can see it's diverging. You see how that sum is getting huge? See that? But if I make that x value inside of our interval of convergence, so even like, should it work at 1? Yes, it should. Let's see. What's happening is 0.36. It looks like that's jumping back and forth. I just have to go further out in the series, but it definitely doesn't look like the last one, right? Okay, and then what if I pick something bigger than 1? I can go all the way up to 5/3. So here, 1.15. That should converge also. But if I go outside of 5/3 to like 2, it should diverge. See? Okay. Let's do this one, a Bessel function. Is that on yours? It's not on yours, is it? It is? Yeah. Okay, it says, now notice the way that this one is worded. It says, find the domain of this function. This is called an order 0 Bessel function. You may run into Bessel functions later in your life. It should not come as a shock to you from this point on to see functions that are written as infinite series. It happens a lot in engineering applications. It's a pretty ugly looking function. This is an order 0 Bessel function. There's higher order ones. There's order 1 and 2 and 3. I think the book discusses it a little bit back in the exercises for this section. But we're defining this Bessel function. Order 0 is where that little subscript 0 comes from. We're defining a function to be that infinite series. And I'm asking you for the domain. So basically I'm asking you for the interval of convergence. And so we need to set up the ratio test on that. And this ratio test on this is not going to be as clean as the ones we've done, but it'll still be the same process. There's nothing new here. Ratio test. Limit n goes to infinity. All right. I'm going to take my time with this one because it's our first time we've had something this ugly. -1 to the n plus 1, x to the 2 times n plus 1, replacing all my n's with n plus 1's, right? 2 to the 2 times n plus 1, n plus 1 factorial, all of that squared, times 2 to the 2n times n factorial squared over -1 to the n x to the 2n. So that is the limit as n goes to infinity of a sub n plus 1 over a sub n with it flipped and rewritten. Everyone see all the n's got replaced with n plus 1s? Now let's figure out what that is. This right here, just so we're clear on this, this right here is going to become a 2n plus 2, right? Same with this one, become a 2n plus 2. So watch the way I write this next line, see if this is what you would have done. I need this to be less than 1, everyone. The limit as n goes to infinity of, let's see, -1 to the n times what? -1 times x to the 2n times x squared, right? X to the 2n plus 2 is the same as x to the 2n times x to the 2. All of this over 2 to the 2n times 2 squared. Oh. Yeah, how the hell are we going to do that? We know we need to peel an n plus 1 off, right? So let me just talk about this over here. If I have n plus 1 factorial squared, isn't that the same as, let me peel an n plus 1 off, n plus 1 times n factorial squared like that? Now, why am I trying to peel off an n plus 1? Because I know over here I have what? N plus 1, or sorry, n factorial squared, and I'm going to want it to cancel, maybe? So by doing this, now the power can go onto each one of those, so it's n plus 1 squared times, well, whatever n factorial is, squared. Y'all see how I wrote that? This right here is very important that you can break that down that way. Yes? Before we did the ratio. Mm, I mean, if we've had n factorial, we've written as n times n minus 1 times n minus 2 down to 1, or if we have n plus 1 factorial, we've written it as n plus 1 times n factorial. I mean, that's what I'm using, right? N plus 1 factorial means it means n plus 1 times n minus 1 times n. So everything from n plus 1 on is n factorial. Okay, you're good? Okay. All right, oh, I need to put this in here. This right here is going to be this. So we have I'll put it in that color too. Isn't that cute? N plus 1 squared, and then n factorial squared. Then up top, 2 to the 2n, n factorial squared over negative 1 to the n, x to the 2n. I need that all less than 1. I get lots of great cancellation here, right? I don't know, maybe it's not great. Negative 1 to the n, negative 1 to the n cancel. X to the 2n, x to the 2n. N factorial squared, n factorial squared. 2 to the 2n, 2 to the 2n. And that's about it, right? Do I need to consider the negative 1? No, because it's going to be absolute value, so I'm going to cancel it out. Even though it's not canceling, it's really just because I'm going to do absolute value, it's gone. And so what I'm left with is an x squared, right, on top. And on the bottom, I've got what, 4 n plus 1 squared? So I've got limit n goes to infinity, the absolute value of, watch the way I write this, 1 over 4 times n plus 1 squared times x squared. So I separated again the stuff that's not with the x that has the n's. I pulled that off to the side so I can figure out what it's going to do. And it's going to do something real nice. It's going to go to 0, right? This right here goes to 0, right? That's going to go to 0. And because that goes to 0 after the limit, this is really turning into something like 0 times x squared has to be less than 1, but that's always true, right? Doesn't matter what x is. 0, something that's going to 0, that's going to be less than 1. Now, look, somebody try and challenge me here. X is, this piece is going to 0, right? When something is going to 0 times this, why can't you then argue something like, well, we've talked about in the past where something is going to 0 and something is going to infinity, that you can't tell what's happening, right? Why can't you make that argument here? X is some fixed value. X is the value of a function, right? You cannot plug infinity into a function, right? I mean, the idea doesn't make sense here. So x is going to take on a numerical value. No matter what you pick for x, n will get so large that this will get so small that regardless of how big you picked your x, this is going to make it go to 0. This will be small enough that the size of that won't matter. Does that make sense? It's because x is a real number as opposed to allowing it to go to infinity. See, there's a difference between that and this. Limit n goes to infinity of n sine of 1 over n. Okay, look at this. This one, 1 over n, right, goes to 0. Sine of 0, 0. So this sine part is going to 0, right? This part is going to infinity. we do not say the answer here is 0. The reason why is because this n is growing, right? It is getting bigger and bigger. It is controlled by n also, right? So it's growing. It's getting infinite as this one gets smaller. Here, this one's getting smaller on the left. That x is a value. It's not, we're not allowed to let it grow to infinity. Understand? I hope that makes sense. I just don't want you to get lost in that, and that you want to try and somehow say, well, why is that not true? Or why can't I, make that like an indeterminate form? What's the answer then? All real numbers. All real numbers. So negative infinity to infinity is our interval of convergence. That's always the best answer, right? I mean, always the nice one, because then that just, well, that one, and if it goes to infinity, then it's just x equals a, but there you don't have to check endpoints. There are no endpoints. So the Bessel function, this is it right here. I won't go through this, all right? No matter what I pick for x, doesn't matter. I add these up. It's going to converge to a finite number. All right, I think I'm going to say that that's good enough. I'm happy with that. Now, part of the reason I'm giving you a take-home test is because that allows me more time to cover the material I want to cover. And so I'm going to begin the next section because we still have some time. So I'll try and motivate this by a picture first. There it is. There's the graph of 1 over 5 plus x. And I talked about this when we first started this chapter, all right? Here's a function, and this vertical line right here is an asymptote. It's where it's undefined. The computer has trouble with that, right? So it just draws a vertical line. And I tried to convince you in the very beginning of this class, or this chapter, that there's a way that I could come in here with these approximations, this power series, and that it starts to get closer and closer to that function, right? Agreed? From that picture, it looks like that's true. Now, if I zoom out, this isn't working. Not quite going down as far as I wanted. Would you agree, from the look of it, that my approximations are getting better and better to the red curve right here, right in this range? But then out here, see, my red one still continues to the right, like this, but my approximations start taking off, right? So it looks like there's this, I don't know, this window in here, right? This interval of convergence, maybe, that I could say. Like there's this interval in which my functions are getting really close, but outside of that interval, my approximation diverges. It goes away from what it's supposed to go to, right? You'll see that? So I'm approximating this function 1 over 5 plus x pretty good within this interval of convergence. If I wanted to approximate it over here, what I'd have to do is change what my a is. In this problem, the a that I have is 0. If I want to change it, remember we talked about shifting left and right? Okay, a change of a would move this over. My interval of convergence would stay the same, but I'd be able to come over here and I would get good approximations for this over here. Unfortunately, this code is not written where I can move it. I have one somewhere. I'll look for it. So I should be able to move that over and then be real good approximations over here within that interval of convergence. Make sense? So the question now for us is, if somebody gives us a function like this, an algebraic function, something we've seen in the past, can you come up with this series? right? That's what our goal is. Because when a computer works on things, well, this would be easy for a computer to do because it just has to plug in values of x and just do some division and addition, or addition then the division to figure out what the value is. But when they're more complicated functions, often a computer is going to turn it into a power series. So how do we do that? 8.6. Representing functions as power series. Recall that good old geometric series, right? Remember that? That thing converged if the absolute value of r was less than 1. And I showed you last class that if we replace the a with 1 and we replace the r with x, right, that we could rewrite this, you go look at last class notes, as this. If a was 1 and r was x. And notice what else happened, and I did address this in last class also, that in this version of the geometric series, n started at 1, and then my power was n minus 1 over here, but if I change my index to 0, then that power becomes n. And then the a is a 1, so it's not there, and this is my r. This will converge when? This is a power series, right? This is a power series. It'll converge when? When x is, absolute value of x is less than or equal to, it's geometric, right? So when did the geometric converge? When r was less than, absolute value of r was less than or equal to 1. So this should converge when the absolute value of x is less than or equal to 1. What does it converge to? What does this sum add up to be? 1 over, right, a over 1 minus r. So a over 1 minus x. And that's if the absolute value of x was less than 1. This is a mighty, mighty important formula today. What's the interval of convergence of this power series? What's the interval of convergence? The interval, though, where it converges. Let's say it again. -1. -1 is less than just this, just that right there. That's what our interval of convergence is, right? On this one? Yes? What if it was 1? What if x is 1? It diverged. And you can tell, look, if x is 1, this is undefined, right? Which means this formula doesn't apply. So that is a very, very important series that we're going to use pretty much the rest of today, all right? So let me show you how we're going to use it. Let's take express 1 over 1 minus 3x as a power series. Express that as a power series for me. Well, according to what I just put in a box up here, right? If I ever have 1 over 1 minus x, I can rewrite it as this power series, right? And it doesn't matter if it's an x or a u. It could be u here, and that could be u here. It's a dummy variable. This is a formula now for us, all right? No matter what this is, 1 over 1 minus whatever, it turns into this sum of whatever to the n, as long as that absolute value of that whatever is less than 1. You with me? So I'm going to rewrite this here. This is equal to 1 over 1 minus, what, 3x? So the 3x is like the u, or like the x it was before. So this should just go straight to the formula. It should be n equals 0 to infinity of 3x to the n. That's what that is. Now let's write out a few terms. Let n be 0, what do you get? Let n be 1. Let n be 2. 3. So on and so forth. Now this is the power series representation of this expression, as long as we make sure that the absolute value of what is less than what. So I'll put here 4, the absolute value of 3x must be less than 1, which means that negative 1 must be less than 3x must be less than 1, which means that negative 1/3 must be less than x must be less than 1/3. So as long as my x values are between negative 1/3 and positive 1/3, this is a great approximation of this function. In fact, it is that function if you could go to infinity. Understand? But it's only valid between these two numbers. Yes or no? Yes? Okay, so let me see if I can show you the picture of this one. There it is right there. Okay, so here's the rational function 1 over 1 minus 3x. Here it is. Let me change my max. Okay, there it is. Here's my approximation. I'm going to start writing out the power series. It was 1 plus, what, 3x plus 9x squared. Now look at my approximations, right? This was the constant 1 function. Here's another linear function, now a quadratic, then a cubic, 4th degree. It's hard to see it, but my little estimations in here are really, really close to what that function's doing, but only between where and where? Here's negative 1, right? And here's positive 1. Only between where and where? Negative 1/3 to positive 1/3, right? Right in this little range, my approximations are dead on, right? They're getting, not dead on, but they're getting closer and closer. Yes? Do you understand the difference visually? Do you see the interval of convergence? Bring that one. So this black one right here comes down, and then right around here, it's really close to the function, the red one, and then it comes back up, and it's really, I mean, it's right there almost. It's off a little bit here. Well, that's okay. I'll just add another one that's even closer, and then even closer, and so on and so forth. Okay, what about something like this? Write the power series for this one. Power series representation of this. Yes. Oh, you got to go? Yep. So does this fall into that format? Not exactly, right? Because we don't have subtraction, right? We have a 3 on top. No big deal. 3 times 1 over 1 minus negative 5x. Right? 1 minus negative 5x is the same as 1 plus 5x. The formula didn't tell me that x had to be positive or negative. So it's perfectly fine if I do that. And then 3 is just a multiple, right? Just bring it out. I can rewrite this piece right here as what? So 3 stays out here times the series, right? N equals 0 to infinity of negative 5x to the n. I'll highlight, this is the part that goes in the series right there, right? That's the part. So that becomes, let's see, equal to, I'm just going to put that 3 back inside, even though I don't need to. Now, I wrote it like this for a reason. It's because for power series, we always like to have the x to the power by itself, didn't we? And then we liked everything else to be like our a sub n, the part that didn't have x in it. So that's why I peeled that -5 off the x. But these are the same. And now we could write out a few terms, couldn't we? I mean, if you wanted to, you could let n be 0 now, right? If n is 0, you get 3, and then the next one would be 15 minus 15x, then plus 75x squared, minus 375x cubed, plus dot, dot, dot. It's an alternating series, right? You just have to take my word for it. I mean, just plug those numbers in. Okay? This one looks like this. Oh, I didn't get the interval of convergence. But you can see it in here. It's right in this little area, right in this little region. What would it be, though? What would the interval of convergence be? Yeah, I'd have to take the absolute value of -5x would have to be less than 1. That's what I would need for the interval of convergence here. So what did you say it would be? -1/5 less than x less than +1/5. Take the absolute value here. Basically, that turns it into a +5, divide through. So the absolute value of x has to be less than 1/5, and then rewrite it. You think you have this? You think this makes sense to you? Yeah? No? Nobody? Nobody's home? Nobody's home. What's that? Oh, good question. Do you have to find the endpoints? This was all based on a geometric series, right? And when R was 1, it diverged. So that means the endpoints, it's divergent at the endpoints. So you don't have to check them. Good question. But it's all because this formula is based off geometric series. And it only works when absolute value of R is less than, strictly less than 1. Okay, what about this one? So again, it looks like it's getting complicated, right? But I can start moving stuff around here. I can say x cubed times 1 over 4 plus 5x to the 7th. Well, that at least I have a 1 up top now, right? I need my bottom left to be a 1. I need subtraction. So the next thing I'm going to do is make that a 1 on the bottom by factoring out a 4. And that makes that a 5/4 x to the 7th, doesn't it? I'm factoring it, forcing a 4 to come out of the bottom. And that 4 can come out in front of the entire thing as a 1/4. Does that make sense? So I have 1/4 x cubed times 1 over, now how should I write this? 1 minus -5/4 x to the 7th. Now that I can write using my formula, right? There's my piece right there that's going to go into my series. Everything else will be outside the series. So I'll have 1/4 x to the third times the series, what? N equals 0 to infinity. What's in here? -5/4 x to the 7th, all to the nth power. I'm not done because I don't like my numbers here to be with my x's. I want to separate these. So I'm going to rewrite this as 1/4 x cubed summation n equals 0 to infinity of -5/4 to the n, then x to the what are two ways I could write it? Or I could do x to the nth all to the 7th. I could do x to the 7th all to the n, or I could do x to the 7n, couldn't I? I'm going to do x to the, I don't know what I want to do. Let's do it this way. That's not wrong, but there's something that we're gonna do. You know what? Let's make it 7n. Sorry, let's make it 7n. Do y'all agree with that? Now I made it 7n. I'm going to bring the 1/4 in here now. Now the only reason I can bring the 1/4 in here is the 1/4 x cubed. I'm going to bring it all in here. Is because the summation does not impact x, right? X is x. So I'm bringing it in here with multiplication. And what it does is this. It goes inside. The 1/4 stays out. Then I have the -5/4 to the n. And then I have x to the 7n. And then I have x to the third. Can I put x to the 7n and x to the third together? Yes, it'll be x to the 7n plus 3. And then over here, what can I do here? Maybe I can do something. Let me see. Tell me if you like this or not. Well, I'll just leave it. I was going to peel out the -1 to the n and have it as its own thing, but I'll just leave it there. That's good enough. And then from here, you can start writing out some terms. Yeah, what would the radius of convergence be here? You need that thing I highlighted up there, or not the interval of convergence, sorry. You need -5/4 x to the 7th, right? Absolute value of that to be less than 1. So the absolute value would be this. So you get rid of the negative on the 5/4, multiply both sides by 4/5, and then what do you think? What, like a 7th root or something like that? 7th root of 4/5? Somewhere between -7th root of 4/5 and positive 7th root of 4/5. Somewhere in between there. All right, I think we've reached a point that we can stop. So I don't, what's that? Say, what do you mean? That's a good question. Here's the thing. This is the formula for, you can use geometric series to create a formula that we can use to rewrite quite a bit of things, right? But not close to everything, right? So the question becomes, is there a more generic way to come up with a series given a function? Like if I give you something different, like let's say I give you sine x. I say rewrite that as a power series. Well, the question is, can you rewrite it as a power series, number one? And if you can, how do I rewrite it? And that's what is so important, or that is the main how do I want to say this? That's what's so beautiful about Taylor series. Taylor series is a formula for coming up with a series. And that's, no, we still need a little more. We need to be able to do some manipulations with power series. Need to know what it means to multiply two power series together, divide two power series. There's some tricky stuff. We have to be able to differentiate and integrate a power series. So if someone gives you a power series, how do you differentiate it? How do you integrate it? And so we're going to do that first, and then that's why I was willing to do the take-home test, because it's going to take us another class to get through the next section, and then we'd be done. We'd only have 2 more classes, and I still need to talk about Taylor and Maclaurin series. So I'd rather talk about Taylor and Maclaurin series and give you a take-home than to not see it at all. All right? So the formula will come, and it's a great formula, and it's one of the main results of Chapter 8. Yeah. All right. And it also turns out that if you have a